Hi everyone, so today you're going to learn about the concept of work as in calculus. The definition of work done by a constant force is if an object is moved the distance d in the direction of an object applied constant force F, then the work W done by the force is defined as W equals Fd. If the force isn't constant, it's changing. We call it a variable force. The definition of work done by a variable force is if an object is moved along a straight line by a continuously varying force f of x, then the work W done by the force as the object is moved from x equals a to x equals b is W equals the integral of f of x from a to b. Work is an important physics concept, so there are a few important formulas that you will need to know. The first one is Hooke's law. Hooke's law says that the force F required to compress or stretch a string is proportional to the distance d that the spring is compressed or stretched from its original length. The formula for this is F equals kd, in which k is the spring constant. Another important law is the law of universal gravitation. The law of universal gravitation says that the force F of attraction between two particles, m1 and m2, is proportional to the product of the masses inversely proportional to the square of the distance d between the two particles. The formula is F equals k m1 m2 all divided by d squared, where k is the gravitational constant. A third law is Coulomb's law. This states that the force between two charges, q1 and q2, in a vacuum is inversely proportional to the square of the distance d between two charges. The formula is k q1 q2 all divided by d squared, where k is a constant. This formula is very similar to a formula for the law of universal gravitation from the previous slide. The units for work in the U.S. measurement system are foot-pounds, inch-pounds, and foot-tons. In the metric system, the units are the dyne centimeter or erg, where a dyne is the force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. Another unit for work in the metric system is Newton meters, which is also called joules.
So for example 1, we have to determine the work done in lifting a 15-pound backpack 5 feet. First of all, we know that the formula for a constant force is W equals Fd. Weight is a force, so in order to lift an object up, you have to lift with the same amount of force as the weight. Therefore, we know that the force is 15 pounds and the distance is 5 feet. Now, all we have to do is plug those values in and we get W equals 15 times 5, which is 75 foot-pounds.
Example 2 is, a spherical papier-mâché balloon of a radius of 0.25 feet is half full of sulfur hexafluoride that weighs 0.4 pounds per cubic foot. Find the work required to suck the gas out through a hole in the top of the balloon, assuming its shape remains constant. So we know that the change in force is equal to weight, which is 0.4 pounds per cubic foot times the volume. Using the shell method, we can divide the sphere into small cylinders so that the volume of a cylinder is pi x squared times change in y. Therefore, the force is 0.4 times pi x squared change in y. We then find the equation of the circular bases of the cylinder. The formula for a circle is x minus h squared plus y minus k squared equals r squared. We put in 0.25 for k and 0.25 for r, which gives us x squared plus y minus 0.25 squared equals 0.25 squared. We factor and end up getting x squared equals 0.5y minus y squared. Since we now know what x squared is, we can plug that in for the x squared in our force formula, which was change in force equals 0.4 times pi x squared change in y. And we get change in force equals 0.4 pi times 0.5 y minus y squared times change in y. Now, we know that the formula for work is change in work equals change in force times change in distance. We also know that the distance is 0.5 minus y. So we can plug in the force we found. And we get 0.4 pi times 0.5 minus y squared times change in y times 0.5 minus y. This simplifies to 0.4 pi times 0.25y minus y squared plus y cubed times change in y. Because the force is varying, we have to integrate the expression for work. The change in y becomes the limits of integration, which are 0 and 0.25, and you integrate the rest of the expression. This gives us an answer of 0.0045 foot-pounds.
Okay. Example 3 says a 50-foot fire hose weighing 1.1 pounds per foot is lying coiled on the ground. How much work is required to raise one end of the hose to a height of 50 feet so that it fully extends? Again, we know that the force equals weight, which is 1.1 pounds per foot times length. So we get 1.1 delta y. The work equals the force increments times distance, which is 1.1 y delta y. Since the force is variable, we have to integrate it, so delta y becomes the limits of integration, which are 0 and 50. So we take the integral with those limits of 1.1 y dy and get 1375 foot-pounds.
The fourth example says a force of 4 pounds compresses a 10-inch spring a total of 2 inches. How much work is done in compressing the spring 4 inches? For this, we have to use Hooke's law because we're dealing with a spring. Hooke's law says that F equals kd. We can plug in the given values to find the value of the spring constant k. The problem tells us that 4 pounds will compress a spring 2 inches, so we can plug that information into the formula and get 4 equals k times 2. That gives us the value of k, which is 2. Now we know that F equals 2d, which we can call 2x. Since work is the integral of the force, we know that the integrand will be 2x. The limits of integration are 0 and 4 because the spring is being compressed a total of 0 to 4 inches from its original length. Therefore, work is the integral from 0 to 4 of 2x dx, which gives us W equals 16 inch-pounds. Now for a U-try. A 10-foot jump rope weighing 0.25 pounds per foot is at a height of 10 feet and dropped onto the ground. Find the work done by gravity. The answer is 12.5 foot-pounds. We hope you enjoyed this video and learned a lot about the concept of work in calculus.